Hello, my people. Hope you're well. This is the fourth and final video on evaluating Riemann sums numerically. And if you're wondering, my gosh, why in the world are there 4 videos on this? It seems rather straightforward. Well, it may be a little bit of overkill based upon my experience as a teacher, because there are just some students, I guess it's the detail-oriented nature of this topic. They just hate Riemann sums. They don't fully get it. They're always making these careless errors because of all of the different varieties of them and the different ways that Riemann sum questions can be framed. So I figure that it's better to be a little bit more exhaustive than not exhaustive enough. Kind of one of those better to have it and not need it than need it and not have it. In this final video, we will be dealing with midpoint sums, which basically, unlike the left hand or the right hand, are not using a function value at the edge of the subinterval to determine the height, but as the name implies, using the midpoint of each interval to determine the height of that rectangle. So let's go ahead and take a look at that. Same function, same interval, same number of subintervals, and so it's still this kind of thing, okay? It's still this right here, 6 subintervals over 3, each of the subintervals being 1/2 unit wide, but we notice that we have to deal with the midpoint. So in the midpoint, if this is 1/2, then 1/4 is right about here, and its function value is here. Between 1/2 and 1, it's 3/4, and the function value is here. Between 1 and 1/2, we have this function value right here at 5/4. And then at 7/4, we have this function value. And then at 9/4, we have this function value. And then finally at 11/4, we have this function value. So let's go ahead and... Now, the advantage is that on a lot of functions, you basically get a little bit better approximation, because the overage and the underage, or sort of this part right here, which overestimates this interval, and this part which underestimates, are almost identical. I mean, they're never quite identical, but they're almost identical, and therefore the midpoint sums are there as a way to sort of kind of split the difference, but there's actually an even better way to split the difference, and we'll talk about that in future videos. But midpoint is our third and final, for this particular series of videos, type of sum that we're going to be dealing with, and you can see how that might give you a pretty good approximation. Cool? Now, we know, again, that the area, all those areas, have a common width of 1/2. And unlike the other ones, we're not going to have f of 0 or f of 1/2. That first one is going to be f of 1/4, right? And then f of 3/4 for the second interval, and then f of 5/4 for the third interval, and then f of 7/4 for that fourth, and on until we get to the sixth and final interval, which is of course f of 11/4. Now, I could calculate all those for you, but I'm not going to bore you with that. I will go ahead and let you know that that winds up being the really nasty fraction of 26/28 over 64, which reduces, but who cares? What we're looking for is the decimal approximation, which is 20.531. Okay. Let's go ahead and do some examples. The 2 examples that we have left in this video are both going to give us irrationals, or at least nasty fractions. So we're going to be doing both of these with the aid of our calculator. Now, this one, obviously irrationals, okay? I am being given the midpoint. I'm being asked for the midpoint Riemann sum on the interval from 1 to 3 with 5 subdivisions. So that makes it a little bit more difficult. And so what we have is we need to carve it up into fifths. Thankfully, the graphing program, I think I exported this from Desmos. The graphing program has given me very easy scaling to be able to do that. Not only to be able to divide it into 5, but each one of them already has the midpoint input designated by one of those vertical lines. So it's going to be really easy. I don't really have to ish quite as much, which is nice, right? And so this is going to be, the height is determined from 1 to 7/5 by the function value at 6/5, and same for the second and the third and the fourth and the fifth subinterval, right? Yeah, part of what takes so long sometimes is just the coloring in, right? Just the drawing. But for those of you who are visual learners, and me, I'm so that way. I'm a very visual person. I mean, one of those people, like, you ask me if you're spelling something right, I have to sometimes write it down. I'm not that dependent upon the visual. I want to be able to make sure that you can continue to visualize, because the more times I show it to you very visibly, the more likely you are in the future to be able to visualize it in your head, right? And so if this is 7/5, and this is 9/5, and this is 11/5, and this is 13/5, then you know that the inputs are going to be here at 6/5, and 8/5, and 10/5, which is 2, 12/5, and 14/5. And you notice that the common width of all of these, and you still do have a common width, although it's not one that you've really encountered before, is 2/5, right? The interval is 2 units wide. It's divided into 5 subintervals, and therefore the arithmetic shouldn't be all that difficult. Each one, because they're all uniform in width, is 2/5 wide. So you need the height given by the function value at 6/5 for the first interval, the height given by the function value at 8/5 for the second subinterval, and on we go until we get to the height for the fifth one being determined by the function value at 14/5. Okay. Now, obviously, we're going to need our calculator for this, and if you plug it into your calculator, you probably are going to want to deal with decimals, since it just makes the keystrokes a little bit easier, right? So when we're dealing with keystrokes, 1.2, f of 1.6, f of 2, f of 2.4, and f of 2.8. Let's go ahead and take this function and plug it into our y1. And so we have natural log of x. Let's go ahead and go back to the main screen. And we know that we do, and let's multiply by 2/5 at the end, okay? And like I said before, it is your choice as to whether you want to risk the keystroke error by including the 2/5 or just regularly. But I would do it the same way I would do it the same way every time, so that you don't actually multiply by 2/5 twice, or not multiply by 2/5 at all. Sort of make a choice and sort of stick with it throughout. So that is just what's in the brackets. And then I need to multiply it by 0.4, and I'm going to get an area that is approximately 1.300. Okay. And that is your area approximation. And because of the way that it curves in the midpoint, it actually should be a really good area approximation. Because you see sort of this overage and this underage kind of canceling each other out, at least approximately, on each of the subintervals as it goes up. Okay. Now, the last one that we have for our example is an exponential. Like I said, we've been doing some pretty Mickey Mouse ones up to this point, so we want to do some that are a little bit more robust. But again, like I said, this is our first entrance into Riemann Sums, so I don't want to totally spook you out. This one is the midpoint sum with 4 subintervals of the exponential 2 to the negative x from 1 to 3. Okay. So we know that we need basically to mark our 3/2 and to mark our 5/2, because those are going to be where basically the break between the first and second and the third and fourth respectively. The midpoint, and this probably is a little bit more difficult to do, but basically if basically it's 0.5 wide, then it's it's 0.5 wide, then it's 0.25, and if each one of these is 0.2, then it's basically just a little bit on this side of 0.2. But the thing is that it doesn't really matter. It matters less the precision with which you draw it, because the graphic is just an aid for our computation. It matters less how well you draw it, and more obviously doing the arithmetic and doing the calculation correctly. This is just an aid to show you those subdivisions, at least approximately, in terms of their general size and how well they conform to an approximation for the area under the curve between those, between 1 and 3 in this particular case. Alrighty. Now, we know that our area, we know that each one of these is 1/2 in terms of its width, and we can factor that out, sort of a GCF thing like we've done before. If this goes from 1 to 1.5, then obviously, and I'm going to be using decimals in here because of, it's going to be easier to do those keystrokes when I actually start using my calculator. This winds up being 1.25, and then f of 1.75, and then f of 2.25, and f of 2.75. Okay. So halfway between 1 and 1/2 is 1.25. Halfway between 1.5 and 2 is 1.75. Halfway between 2 and 5/2, or 2.5, is 2.25. And halfway between 2.5 and 3 is 2.75. That should be pretty straightforward. So let's go ahead and plug it into our calculator. So 2 to the negative x. Let's go back to our home screen. And let's do y1 at 1.25. And then y1 at 1.75, and look up at your screen every once in a while and make sure that you're not, forgetting a paren or something like that, because they do, go off the edge as you keep going, right? So make sure that you look up every once in a while and you're not just focused on the keypad, because you can make a mistake that way. So basically, what's inside the brackets works out to 1.07662498, but we want half of that. And we find out that our area approximation is 0.538. Now, is that reasonable? And actually, it is. Okay. Now notice that this interval is too wide. And if you were to draw a line, and this is, approximately 1/2, and 2 times 1/4 is 1/2. If you were to draw a line straight across here at 0.25, you would see that you have approximately as much over as under, and therefore what you've done here is a reasonable calculation for what the area of those rectangles would be. Okay? Now, before we adjourn, these are only 4 videos and one small sort of sub-series of videos for the unit on Riemann sums and area approximations, as we're sort of on our way to dealing with integration. There are other ways to approximate the area under the curve. Some are more formulaic than others. We have focused on just 3 of them here and only doing them numerically. Okay. But this video does basically give you, like it says there on the sheet, the meat and potatoes of Riemann sums. Okay, we will pause for a moment in the next couple of videos and review sequences and series, because we're going to need some of that notation, specifically sigma notation, those summation formulas that you may have seen before, when we come back to the Riemann sums and we actually start calculating those Riemann sums and evaluating them using the sigma notation, and ultimately applying limits to those sigma notations. We will then basically step away and deal with other Riemann sum problems, ones that are less formulaic and lend themselves much less to using sigma notation, but you will encounter nonetheless. And I just want you to not be surprised when Riemann sum questions come at you in a weird way. And then lastly, we will be doing a section from chapter 7. For some odd reason, Stewart puts trapezoidal rule with a lot of the Calculus 2 material. It's unnecessary. It's related to this. Some books actually do the trapezoidal rule when they do, or in the same chapter that they do Riemann sums. I would like to do them together because they are related to them. We have done these videos today, number 1. There will be several videos for number 2, number 3, number 4, and number 5. There's actually already existing videos for the trapezoidal rule. I'm going to go through those and make sure that I like them. And if I do, I won't do any new ones, but if I don't, then I'll definitely supplement them. But that is kind of where we are headed over the next couple of days. And once we are through with 1 through 5 of that, we will actually get back to the mechanics, and we will turn towards what is called the definite integral. And I will show you sort of how all of this Riemann sum stuff links up with the definite integral and using it to find the area under the curve. So that brings it to a close. I will see you in the next video. Bye.